Landing on a ship. An important piece of landing equipment must be thrown to a ship which is moving at 45 centimeters per second before the ship can dock. This equipment is thrown at 15 meters per second at 60 degrees above the horizontal from the top of a tower at the edge of the water. So you can see it's 60 degrees with respect to horizontal, 15 meters per second it's thrown towards the ship. 8.75 meters above the ship's deck, so that's this distance. For this equipment to land at the front of the ship, at what distance d from the dock should the ship be when the equipment is thrown? So since the ship is approaching here, so when this is thrown, it's going to fall here, and at the same time, the ship must have traveled towards the dock. Okay, so what should be the distance d when it is thrown? So we have an initial velocity x component, v0x is equal to 15 meters per second times cosine 60, that is 7.50 meters per second. And we have an initial velocity y component, v0y, that is 15 sine 60, and this will be equal to 13.0 meters per second. Okay. Now, this is how we can visualize the situation. Here we have a projectile that starts with initial velocity v0 making an angle theta with respect to horizontal at a distance h0 from the ground, and that's basically from the ship. And this is going to be following this path and complete its motion in a projectile range of x sub t. So first, what do we need to do? First, we need to calculate the time of flight. So how long does it take for this object to reach the end of its motion? Time of flight t sub f. Okay, so the y component of the velocity vy will change as a function of time. Initial y component v0y minus gt. This is basically under the influence of gravitational acceleration. When we have y is equal to h0 plus delta h, so delta h is basically what I have labeled the maximum height above the level where it was thrown that it's going to reach, h0 plus delta h, v sub y will be equal to 0 meters per second. So we will have the initial component v0y minus gt prime is equal to 0, which means t prime, the time to reach the maximum height, will be the initial velocity y component v0y divided by g. And at time t is equal to 2t prime, what will happen? The velocity y component at 2t prime will be equal to minus v0y. So this is basically we travel a distance delta h on the y-axis and we come back. So this is at this level here, and we have the same y component in the negative direction. So it will be in the opposite direction. Now what will happen? For t greater than 2t prime, the velocity vy of t will be minus v0y, which is its initial value at this point, minus gt. So delta y, this is going to be the distance we travel with this velocity, will be minus h0. We start at h0 here, so this is starting at h0, and we're going to 0 y, so that's delta y is minus h0. This will be the integral from time t equals 0 to delta t. So I have reset my timer here so that time t equals to 0 now corresponds to this point, right? So that is from my initial timer it was 2t prime. Now here I'm assuming that I'm starting this motion with minus v0y and it's going to fall down. So this is the delta t will be the time it takes to reach the ground starting at this point. So this will be integral of minus v0y minus gt dt, and that will be minus v0y delta t minus 1 over 2 g delta t squared. Okay, and h0 therefore will be equal to v0y delta t plus 1 over 2 g delta t square. So we can write this as delta t parentheses squared plus 2v0y delta t divided by g minus 2h0 over g equals to 0. So basically I have multiplied this equation by 2 over g and collected all the terms on the right hand side. So this is what I obtain, a quadratic equation. So the answer will be delta t is equal to minus b, which is minus 2v0y over g, plus we won't take the minus sign because the time interval should be positive. So plus square root b squared minus 4ac 4v0y squared over g squared plus 8h0 over g divided by 2a, which is a is equal to 1, so it's 2. So you can see that delta t becomes, from this calculation, minus v0y over g plus square root 1 over 2 will come as 1 over 4 into the square root, so it will become v0y squared over g squared, and 8 will become 2 because I have 1 over 4 coming from 1 over 2. So inside the square root it becomes plus 2h0 over g. So with that, the time of flight will become becomes 2t prime, the initial time to reach the maximum height and to reach the level where I have thrown it, and delta t, the additional time required to reach the ground level. So this will be 2v0y over g. So I substitute for 2t prime 2v0y over g. So 2v0y over g minus v0y over g plus square root v0y squared over g squared plus 2h0 over g. So this is my time of flight. So 2v0y over g and minus v0y over g, so that will make v0y over g. So you can see that the time of flight becomes finally d0y over g plus square root v0y squared over g squared plus 2h0 over g. So this is all inside the square root. So the range of the projectile we can now calculate. The range of the projectile is what I call, in my figure here you can see, is x sub t, x total, the displacement on the x-axis. This is the x component of the initial velocity times the time of flight. Because the x component doesn't change in time, there is no acceleration on the x-axis. So for it to land at the front of the ship, we have a requirement. So I call V sub s the ship speed, so the distance d, that's the initial distance between the front of the ship and the dock, minus the distance the ship travels during the time of flight, v ship times tf, must be equal to the range of the projectile motion, x sub t, so that it's going to exactly land at the front of the ship. So this d will become the total range, x sub t, plus the speed of the ship times the time of flight. So x sub t was initial velocity x component times time of flight plus the speed of the ship times time of flight. So you can see that d will become, in time of flight parentheses, v0x plus bs times time of flight. So v0x was, if I go back here, it was 7.5 meters per second. So it is 7.5 meters per second. The ship was moving at 45 centimeters per second. So it is 45 times 10 to minus 2 meters per second times the time of flight. Now, for the time of flight, I have to now calculate this. I have 15 sine 60, that is v0y, divided by g, that is 9.8, plus square root v0y over g squared, so it is 15 sine 60 divided by 9.8 parentheses squared plus 2h0, 2 times 8.75 meters over g, that is 9.8, and if I do this calculation, the answer I find for D is 25.5 meters with 3 significant figures. Okay, so let's summarize what we did here. This ship is traveling towards the dock, towards the tower here, with a velocity 45 centimeters per second to the left. And we have a projectile making an angle of 60 degrees with respect to the horizontal, with initial velocity 15 meters per second that is thrown, and the tower is 8.75 meters tall. So we want to make sure that this projectile will land exactly at the front of the ship, so that the ship will have traveled a certain distance to reach that point here. So first we have found the x component and y component of the initial velocity. Then we have noted that after starting the projectile, this object will reach a maximum height delta h above the level where it was thrown. So we have calculated the time it takes to reach the maximum height and to go back to the initial level. That is basically 2v0y over g, 2t prime. Then we have reset our timer. You calculated the time it takes for it to reach the level of the ship. So this is basically a distance, a displacement of minus h0 that's traveled with an initial velocity minus v0y, initial velocity y component minus v0y, minus gt, the acceleration, minus g times t. So solving this equation, we find that delta t is given by the root of this quadratic equation here, and the total time of flight is 2t prime, the time to reach the maximum height, the time to reach the level where it was thrown, and then the additional time required to fall all the way down. And when we multiply v0x with this time of flight, we obtain the projectile range. And for the object to land at the front of the ship travels a distance, speed of the ship times time of flight during this time interval. So d minus vstf should be equal to the projectile range. Solving this for d, we obtain 25.5 meters.